I say you can never have too many blinking lights on a project like this. Hi. A couple of weeks ago, I posted a video showing how I had modified my Project 65 breadboard computer to play music. Today I wanted to follow up on that, focusing on a particular piece of the project, in particular this breadboard, which I've been calling the expansion board. This board provides a couple of 8-bit I/O ports, well, output ports anyway, that allow the computer here to talk to the audio generator over here. And this was a project that kind of got away from me a bit. You may have had this problem yourself from time to time. You start a project, you get it working, you think it's just about perfect, and then you realize right at the end as you're documenting things that maybe you went about the whole thing in the most complicated way possible. And that was this project for me. So today I'm going to talk a little bit about the first version of the card and what I did in the first place, what I should have been doing all along, and then we'll talk about some of the updates and upgrades that I've made to this and demonstrate them. Now, if you've worked with 6502 breadboard computers before, the first question that might come to you is, why didn't you just use a 6522 VIA? The 6522 is sort of a companionship to the 6502 CPU. It provides a pair of 8-bit expansion ports that you can use for input and output as GPIO pins, as a parallel port, whatever you want. In fact, I do have one right here. I use it to control my serial port and my disk controller. But I only had one of these on hand, and it's kind of in use. I kind of got inspired to do this project at the very last minute, in sort of the week before Christmas. And so it was very important for me that I be able to put together using components and pieces that I already had ready at hand. The entire audio generator circuit, for example, was salvaged from another project that I'd been working on a while back. And for I/O, I needed to find something that I had in my box of components that I could use to talk to it. And that led me to these 3 chips. These are 74 HCT 574s. So let's talk about those for a little bit. So the 574 is a pretty simple chip. It's an octal edge-triggered D flip-flop. One way to think of it is that it's just a single byte of memory that sits on the data bus of the computer that the computer can write to, and a peripheral device like my sound generator can read from. So if we want to think about how we're going to hook this up, there are 8 input lines, and those are going to be attached to the data bus of the 6502 computer. There are 8 output lines, and those are going to be attached to the sound generator or some other peripheral. There is an output enable line which turns these on or off. Now, I want those to be enabled all the time, so this is just going to be tied directly to ground. And then there's this input called clock, and this is probably the most interesting one and the one you have to think about most when interfacing with this chip. When clock transitions from low to high, that's when whatever data is on these input pins gets copied into the chip's internal buffer, those 8D flip-flops, and becomes available on the output bus. Now, since this 574 is going to be a memory-mapped device in my computer, it makes sense to compare it to some of the other memory-mapped devices, like the static RAM that I'm using. I use one 32 kilobyte static RAM chip, and there are a couple of important differences between the way the 574 works and the way the static RAM chip works. For one thing, the 574 only has this single clock input to control when it's written to, whereas the static RAM chip has 2 inputs, one called chip enable, which I use for my address decoding logic, and one called write enable, which controls basically the timing of when it's being written to. So for the 574, I have to combine both of those tasks into a single input. The other difference is that for the static RAM chip, the write enable is an active low signal. It goes low when we want to perform a write. And for the clock in the 574, it's an edge-triggered positive signal. And I think I kind of conflated that positive edge-triggered signal with an active high signal as compared to an active low signal when I was coming up with my control logic. And I think that led me to do a few things in a more complicated way than I necessarily had to. So this is the first version of my control logic for the 574 clock signal. And I'm generating that signal out of 3 inputs that come from the 6502 computer. The first one of these, RWB, comes directly from the CPU. And this is simply an output pin that is high when the CPU is trying to do a read, and it's low when the CPU is trying to do a write. The second one is this chip enable expansion board. And this comes from the address decoding logic, where it was easy for me to get a signal out that goes low when the CPU is trying to access the memory location where we've decided that this expansion board should live. The third input is Phi2, which is the system clock, which in my Project 65 computer is a 4 megahertz clock. And this is used to control the particular timing of when we want to do a write. And the idea will be that we want to do a write, which basically means that we want this signal to go high when RWB is low and the chip enable is low, and when the system clock is high. In order to understand the role that this Phi2 system clock plays in the memory write, you have to look at the timing diagram for the 6502, which you can find in the datasheet. Unfortunately, this timing diagram tries to combine every single sort of memory operation that can happen into a single diagram, and it becomes very difficult to read because of that. But note at the top here we have Phi2, and during a single memory cycle, Phi2 is low for the first half and high for the second half. And during the first half, that's when the memory access is being set up. It's when the address lines are being set. It's when the RWB signal goes low. But things aren't quite ready yet. And that's why, for example, with the control logic for my static RAM, the write enable signal goes low for the second half of the clock cycle. And that's when it does its write. And I was thinking, since that was active low and since the 574's clock signal is active high, I basically wanted to do the inverse of that. I wanted a signal that would go high for the second half of the clock signal. So that was this 4-gate NOR solution. Now, this version of the circuit almost but doesn't quite work. It does try to write something to the 574 chip, which honestly means that a lot of things are working correctly. All the address decoding is working. We're dealing with the RWB signal correctly. But most of the time, the data that got written to the 574 chip was random. Once in a while, it would be the correct value. It was working just enough to make me convinced that I still had a timing problem. And if we go back to the timing diagram here, we can kind of see the timing problem. It's this right here. It turns out that there is a delay between the beginning of the second half of the clock cycle and when the data that is to be written is actually going to be available on the data bus. And in the diagram, that time is called TMDS. And if we scroll up a bit, we can see that TMDS for a 6502 with a 5-volt power supply is 25 nanoseconds maximum. So there's 25 nanoseconds between when that clock cycle reaches its midpoint and when the data is actually there to be written. Now the 574 also has something it calls a setup time, which is that it wants that data to be available on the bus for about 20 nanoseconds prior to triggering the latching with the positive edge of the clock signal. So that means, all told, instead of the clock signal for the 574 going high here at the midpoint of the clock cycle, we need to delay it by at least 45 nanoseconds so that we do it here when the data is actually valid. And that leads to this version of the control logic. The top half here is exactly the same as what we had before. It just adds these 4 additional gates at the bottom, and each of these is set up to be an inverter. And because there's an even number of them, they all cancel out. And the value that we had here is the same value we end up with here for the 574 clock. It's just delayed because it takes time for a signal to make its way through each of these gates and for each of these gates to change its outputs. And for these 74HC02 chips that I'm using here, and here I'm using 2 of them, I'm using every gate on 2 of them, it takes about 7 nanoseconds for each one of these gates. So that's a total of 56 nanoseconds, which should be enough and give us a little bit of leeway. And this version of the board works. This is the version that I used for the Jingle Bells demo that I posted just before Christmas. It's a perfectly valid circuit, it obeys all the timing restrictions, and it works. It just feels like it's taking a very roundabout sort of path to get to where it's going. And that kind of led me to take another look at the datasheet for the SRAM I was using and a few other sources, and really think about what that write enable they were using, how that worked. So what I mean by that is that it looks like the SRAM isn't latching its data here in the middle of the write cycle where its write enable signal begins, but doing it here at the very end, where the write enable has a positive edge. It goes high again. And as you can see, the data that it needs, the write data over here, the address lines over here, that's all still valid for a while after the end of the clock cycle, until this time called the hold time finishes. And so that led me to think that maybe my 574 logic could just do the exact same thing. It could go low here in the midpoint, and go high and latch its data over here, and just be high the rest of the time until the next write happens to occur. So that led me to this final version of the expansion board. And in this case, for most of the address decoding and control signal generation, I'm able to use logic that exists already on the main board of my 6502 computer. This circuit here that generates the write enable signal is exactly the circuit that generates the write enable signal for my SRAM, just using the Phi2 system clock and the RWB signal from the processor. And this is the address decoder that the main board is using. It uses a 74HC138, which is a decoder demultiplexer that works with the top 3 bits of the address bus and basically divides the address space into 8 kilobyte chunks. And so there's a particular output line that I've been able to hook up to the expansion board. There's one here for the 6522 that I use for I/O. There's one here for the 8 kilobyte ROM that I'm using. So over here on the expansion board itself, the logic gets a lot simpler, and because of that, I was able to have some room for expansion. So instead of using a single 574 like in the first version of the board, this version has 3 of them. And so it has 24 output lines that can each be controlled individually. For the output decoding, the chip enable for the expansion board is just daisy chained into a second 74HC138. And this one is fed the 2 least significant bits of the address bus. And it generates one of these output lines. So one of these 574s is going to live at memory address A000. This one is going to be at A001, and this one is going to be at A002. And the result of the address decoding logic then is just ORed with this write enable signal. So if the address decoding isn't set up to activate this chip, nothing ever happens. The control line stays high all the time. If the chip is enabled and a write enable signal happens, then this 574 clock output will go low at the midpoint of the clock cycle, and it will go high and latch its data in at the end of the clock cycle, when the data is still valid until the end of the hold time. So this was how I did the final version of the board, and we'll see that in action in just a moment. Now, both of these versions work, and I'm not entirely sure which is the best one. I'm sticking with this one for now because it gave me the room to expand and have 3 output chips, which is really helpful. But it is kind of pushing things in terms of the latency of this circuit and the hold time. Now, I saw some threads on 6502.org that kind of made me feel comfortable with the idea that the data would be valid on the data bus for quite a while, in addition to just the minimum guarantee of the hold time that the processor has. I'm pretty sure it would be possible to rearrange the circuit a little bit so that there was less latency, so that the system clock was only going through a single gate in order to generate these 574 output clocks. But since everything's working, I don't feel a strong need to do that right now, and it would require some additional logic gates here on the board to handle each of the individual output chips. But that would be a possibility for the future. The previous version, I think, is actually a little bit more rigorous in terms of doing the right thing in terms of timing, but it took up more space. So in any case, since I'm acting here as a hobbyist, and since I'm a computer scientist and not technically a computer engineer, I feel like I can go with what works in this case, and your mileage may vary. Feel free to comment below. But for now, enough talking about how this circuit works. Let's see it in action. So here's the new version of the board all hooked up. We have power lines, the data bus, and up here the 4 control signals, the write enable, the 2 address lines that we're using directly, and the expansion bus chip enable. And now with the sound generator connected, we can produce a little bit of music. Now the only problem is that the audio generator is only using 1 of the 3 574s. It only needs 8 bits of input. So let's see if we can come up with something that will show all 3 of these working simultaneously. Okay, so I didn't have enough parts left over to build another voice for the sound generator, so I've resorted to that old fallback. We're going to make some LEDs blink. I have 3 chips, so 24 output lines, so I've hooked up 24 LEDs, and I've written a little bit of code to make them blink out in some different patterns. Well, I think that covers it. Thanks for watching.